if there's,
yeah, now there's this action.
Okay. Perfect. Are we good? It looks like it's running. Thank you. Okay, thank you for coming. It's a pleasure. I'm going to talk about developments in quantum and ways of building computers or doing quantum talk, or maybe touched on Clifford's talk after mine. Start with a bit of, so I'll tell you a little change in the field over the last years or so. Years ago, that almost groundbreaking research on computing was done in an environment here at McGill. For the last decade, it's become more and more common. Private have started to and do research, and so this is in the landscape, but still an enormous amount to do as academics learn about this area and to gain understanding. So the code I wanted to start with starts with as a student in 2000 was at McMaster University, which is in Hamilton, Ontario. And the physics department sends someone as a rep to the Canadian Under Physics Conference, which is undergrad physics have a grad fair where universities send reps to try to attract futures. And that year, the physics conference in Winnipeg, which is my home, and so to go as their rep. And it was this undergraduate conference. There was going to the GRE, the grad examination. If anyone grad school in the U.S., typically you have to write exam or two types of. And it was the same time as the physics conference. To get there somehow. So I asked around as going to this GRE exam, and I found one person who had a picture from Saskatchewan. So he University of Regina and his job. We got talking this GRE way back, want to do in the future. And one of the things that came, okay, maybe that I would love to do and he said he really go to a big university and also in this area and coming at the time. This guy's name was, and people in the audience fun because is someone who is very masculine and successful. And in Chad was a Chad. So I took a more path. I went through I went to Switzerland, came back to the Institute for Quantum Waterloo, and then eventually landed McGill. Chad went to initially university, and then he worked for IBM, private sector. At IBM for a couple of years, found his own computing company. So he found some computing compass that took his name, Chad Rigetti, and he is Rigetti Computing. Company sort of an explosion because of, I mean, difficult to know how market or why, but we can think of it as a potential view on prospects for the future. And if you, on that view, or you believe, then the future of quantum become much, much better humans. Chad's company eventually reached a market of about $5 billion. Then there was a big crash, drop, and I don't know in the news about why this crash in quantum computing happened, because of NVIDIA, Jensen Huang, actually at the computer show, decided to give his view on how long it would be useful quantum. how many expected it would be before some computer that could realize that our classical computers couldn't hope. And he fears the stock, so maybe 5 billion isn't really justified. Go and look at experts say it will be before we can do something that something truly used classical computer couldn't. Survey that is conducted by IQ based. And this survey of experts across the world, quantum computing and question, very well defined. So, do you think it will be? There is a quantum that can encryption, RSA, a crypto scheme, the cryptography scheme that's used in transactions and daily use. So many years would it be if RSA encryption key of bits? RSA encryption relies on the hardness during a number's prime. Experts weigh what they feel is going on and guess what is the time scale. Pretty much said or thought 23 when this was to happen within 5. The majority feel that it would be to 20 years away. Jensen Huang's are not so unreasonable. You could ask, okay, why 15 to 20 years still not there? We know in principle this problem. Why can't we get some today? I was serving on a defense committee for some mechanical engineering, actually. Studied this question, practical standpoint, figure out how long would it take RSA on a classical computer, and then how long would it take a computer? So you can ask the question, how many operations or do you need in crack or 1,000 hours? And the answer, 1 exaflop. Exaflop is the roughly computing power of the most known cluster, El Capitan. If you have a 2,000 key, it turns out that it would significantly. So roughly years, you ran a series. 1 million of these in 24 hours, or 100 million of these in 24 hours. For a quantum computer, the same kind of estimate. Know the algorithm used to factor these large. That algorithm is shown, and estimates have put physical qubits to do this in hours at 10 million. And that might sound like a, but if you think of resistors, each chip, there are 1 billion individuals. And so if you put a computer with quantum that are very high, meaning that they have less than 1,000 operations, then you would only 10 million of those. Right now, state-of-the-art quantum compute, these errors, 1 in operations, getting to 10 million. Okay, 10 million qubits, if qubits are relatively meter on a side from qubits, you need a platform that's about 10 meters, so a 10-meter array of qubits. And together and make large scale is of our day, quantum computing. Okay, so that's of all of the key things that I should mention. Factoring large numbers in cryptos is the only thing a quantum, there are many examples where quantum can help us learn physics. It could help material science. Everything fun, small scale, and short is quantum, about chemistry, and potential discovery, and many other uses of quantum computer. But what could it allows a quantum something with so few compared to transistors in a supercomputer. It's really this exponential growth. If I simulate, and ultimately every patient is some kind of simulation or ideation of quantum solution. If I have a quantum system with resources, it turns out I need essentially large classical resources to simulate that. And the exponential just goes up fast, so fast. Only simulate moderate quantum mechanical system on class, whereas quantum simulate those quantum, believe that we can do sources that scale linearly. I drew an indicator, a very polynomial, but you can imagine the line, sure, but it's dramatic than the exponential. So what is this and where does it come from? You may have heard that in physics we have this thing, position principle, that quantum can behave are in two states. It's not really true, it's just the way. The more precise way is that know how to write down expression for a quantum, but it takes more than it would take by the classical, okay? So if we have it has states, 1 and 0 distinguishable. It can also be an addition of any of those, and that superposition of numbers, okay? So it takes just 1. If you have 2 quantum Bohr numbers, which are complex coefficients that go in front vectors, so you have numbers that you need in order to quantum bits. And up and very, very quick, even if you only quantum bits, to get a classical quantum state in, you need about a memory, assuming you're using per state. And then it goes up very quickly after qubits, and after qubits you get a tera. Maybe that's the size of state drive. But then if you get larger than that, very quickly gets to reach the max capacity of the hard drives in old. At a scale of about just to just quantum mechanical classical hard. But we know that everything mechanical. Atoms, all the everything is quantum mechanical. Can exploit that and control it, store it. We let that quantum know what state it has, and then questions. And that's what a quantum. You give it some question, you allow it to explore its space, and then you ask it. Okay, it's not easy. You take some that you can control, systems you can control big like this, and then convert them into something. That's something beautiful characteristics in a king's, but it's also like the wings of a butterfly. Okay, so you can manipulate objects, some of in the lab, into something beautiful, some crazy thing otherwise possible, but they're very degrading. And so we need tricks to make that. We need special tricks to fly alive. One of the things you can do is you choose a good system to write zeros and the 1 quantum computer. So this is a quantum computer state and grounds some state of a supercurrent is flowing one way. Some very states of light. But here I have my favorite character. Okay, so got 2 states of Olaf represents a qubit. two different systems that represent ones in your quantum. And if we just had an error occurred, brings his friends, then we can build C. And in a quantum, you will to errors with equal physical qubit and enormous redundancy. You need this redundancy. You want to be able to the presence of errors in the computer to so you look for where it's occurred, out what error has occurred, undo it. Quantum computer can and expressing. So if we have redundant encoding, then Olaf's is bad, some error occur. We can do some kind that knows off was hit, error occurred, and is the beauty of what's called Florence. Turns out the probability of making an error in individual qubit below some critical probability, increasing this quantum computer by some amount, an exponential of making a mistake in quantum computation. That's accuracy theorem, and that is the sauce computing. So I'll show some graph, scary at first, but I'll explain it. So this graphulation of a quantum, what would happen in a quantum if errors that occur with some probability on the horizontal given by epsilon. So there's some unit time that each of them be messed up. And on the vertex is the probability encoded qubit has an. So you can think horizontal axis is the one of those Olafs becomes, and this is the probability that Olafs knows or become. And if you make a quantum error above the threshold, critical threshold, then the error worse and worse and worse, okay? Above the critical, detect errors faster and they just propagate, whole quantum computer falls off. But below, this is a logarithm, powers of 10 on this. Below, it turns out that you could have a system where is a description of the qubit, or then of logical qubits in one logical. All the size of this is linearly with little advantage. This is something that was, or this theoretical, summer. There were real experiments that came out, private companies. They invested a lot of money. The experiment happened where they took 100 in their little quantum computer. And their toy quantum computer, they could sub-regions, subset of those qubits. Let's use all bits to encode logical qubit. And play with the size of the error. They're larger on purpose, and just see as a function what happens to the qubit. And they made this plot. And if you go to error rate, it's called mean detection, there is an increasing in the probability, or an increasing in a mistake. So that value, you get actually decreasing. What does this exponential error mean? It grows the quantum a little bit to the quantum states almost forever. Quantum states that live ever, and you can quantum states of an enormous amount. But this cannot in the same way. It cannot be that you just name type of chip that substrate must be future that was distributing the across different chips. Is that the wires take up the control much space. We distribute the quantum compute different nodes, and for we will need something like that. And the quantum network can have qubits, or might have collections of between those qubits and information to the other. One way to information, the advantage of entanglement. So there Narcisse, Manitoba, where I grew up in Winnipeg. You may not know this, but Eve is the capital of the largest collection in the world, and it's time. So if you wait about, you go through early May, you will find enormous entwined. The male snakes try to snakes, and they form these. But the snakes are entwined with each other, coiled. Quantum states correlated with each other, entanglement. They are separated, qubits are separated. You can arrange for those two qubits perfectly in such a way that something over here, operation over here, and you do you can send information what happened over here. This is teleportation, and one of the quantum teleportation speaker, Claude, is a co-author that introduced the concept. So teleport has been used to do very small quantums, different points in space by several meters. So an experiment that was done very recently had a tron over here, a trapped ion over a different spot, and they would send photon trapped ion and the ion to some detection line, clicks in the detect, fantastic entangled quantum state, some kind of teleportation, generates an operation similar to what you would expect in a quantum computer, but at a distance. Okay, so this allows us to do these operations. There are others people are using beyond this entanglement to distribute quantum nations over losses, and another is to just use for your qubits. Instead of using in solid states or individual atoms, the Xanadu, which is the company Toronto, has registered a prototype shown in this, where they can about physics, but those qubits involve no matter. They're purely a state of light. And to do, you need a complex of photons that guide ways of entanglement between and ways of measuring single photons with chambers. Photograph of their device or server racks. And if you go from 12 qubits, that might take a lot. Other company, something where they just light, is Quantum. Quantum is a company that around the world, they have in California, they also a base the UK. They are open new enormous one in Brisbane, one mill in Chicago. They intend to build the scale quantum computers. Quantum computers have been active, and it's also in the States, qubits. But in order to they are schemes where they detect the state photon, and to detect the photon, you cool your detector very low temperatures and need liquid helium. And so they built cryogenic chamber, just a small prototype in the end. They're modules that are shipping containers filled with liquid helium. And if you believe that they show about 100 of those modules in this warehouse, warehouse. They'll have two warehouses, one in Brisbane. We estimate that they have about meters in each of these. Meters is about the amount that's used by MRI machines. About 100 shipping container size elements, 500 MRI liquid helium. There are less than MRI machines in the country of Canada, 400 and some, and is a non-resource. When helium is released in the atmosphere, it is very difficult. The only way that we can get it, gathering it from a byproduct of fossil fuel. And so if we could do that kind of thing and not involve cryogenic, cooled. And so I'll tell you about a project my group at McGill are trying to relieve ourselves of cryogenic. So again, we want to send from one place to these of light. Instead of doing it with which are tiny equals of light, imagine doing it bursts of classic. So classical light, superposition classical light, kind of like having a suit of two macro distinguishable states, to what you've heard about Schrödinger's cat. Schrödinger's cat is an example that illustrates the preposterous quantum mechanics. It is locked in a box vial, the poison vial open if inherent in its excited to its ground state. Okay, if you wait for half the time of the atom, says you are actually in some mechanical superposition of having the decade and the cat alive, and the atom and the cat dead. And since the cat alive are very diffroscopic classical, it looks preposterous, but it's also quantum mechanics. So how is such a cat alive state? I think I won't go else, and in fact, I think skip my next slides. But I will just mention that light carried in such a state it is classic. A classical source like microwave source on your qubit. If the qubit is state, a situation where light passes through. In the excited state, a new object that looked at, this effect, that allows you the direction of the light, perfect reflection of a classical light. Qubit is in the excited. And if you prepare superposition of the ground states of Schrödinger's cat, where the added superposition of ground states, superposition of having light off cavity is your qubit. Okay, so just like cat dead, use of classical light that or back a cat qubit. Do this and it's become much simpler. You can use are appropriate for classes of light that are much easier room temperature that require cooling and all of them. So the solution that I can give you, distributing rotation over long distance without doing this cooling is maybe cat states. And that's just what you can do with barometer, where you interfere and then you can delay. I wanted to end with my favorite novel. So I don't know if any of you, it's a Vonnegut called Cats. Vonnegut's brother was this, and Kurt Vonnegut, an appreciation of the basics of physics and geophysics. And he imagined in this that there would be some phase of ice water 9. Phase of ice water populated to be at room temperature atmospheric pressure. And if you know anything of conditions, if you prepare a particular phase stable than the surroundings, and you place other material will sort of wait that is and take it up. Place a little piece 9 in the novel, the ocean immediately solidify. Is pretty clear from the novel based on of nuclear weapon. If you think of the danger with cryptography to crack of the existing systems, sure quantum allegory follows as well.
Exactly, yeah. And connected to the hour. Yeah, perfect. So yeah, it's gonna like record you.
Welcome, everyone. Yeah. So it's pleasure to follow up on Bill's talk. It's funny because we did not really consult each other exactly on what we're going to talk about, but I think our two talks are extremely complementary, which is great. So I want to tell you about quantum information, a little bit about the history of quantum information to the perspective of someone who's been in it for nearly 40 years, since the 1980s, and tell you about the impact of quantum information on privacy. So we all heard that quantum computers are going to crack our favorite crypto systems, and so we all fear of the impact of quantum computers. But we've also heard of this thing called quantum cryptography, which seems to bring something positive. Now, I want to tell you a little bit more about all this. And I'm going to actually answer the question, is quantum information a friend or a foe to privacy? Now, to get you there, I want to do a little bit of history. So Bill's presentation was really about the recent stuff, and some of mine is really old. So I'm first going to tell you about privacy and tell you that back in the time of Julius Caesar, he was using encryption. And this is written, there are documents explaining exactly what Caesar was doing. Now, his system for encryption to get private orders that he would distribute to his generals is what we now call the Caesar cipher. And the Caesar cipher is an extremely simple-minded system where you take the letters of the alphabet and you shift them by a fixed number of positions. Now I have this slide here that shows you a little bit how one can do that. So this wheel here maps together internal letters and external letters, and right now we have the letters of the alphabet matching to themselves. Now in Caesar's cipher, the letter A was mapped to D, B to E, C to F, and so on. So there was a shift of a small number of positions in the alphabet, and that was it. That was the system. So to do the encryption, you would shift the letters a little bit in one direction, and to get the messages as they originally were, they would be shifted back by the generals to make sense of them. Now, this is 2,000 years ago, so people couldn't even read, most of them. So encryption was prevalent because people couldn't read, but this was good enough, and he actually used that for a while. But as you can imagine, such a system was cracked pretty fast. And so people had to come up with better ideas. So I have this small equation here. If you take the word Caesar and you position-wise add the number 3, which is corresponding to letter D, it gets you to FDHVDU corresponding to Caesar, and the right-hand side here is the so-called ciphertext corresponding to Caesar, the plain text, and we call this the key. So the key in the Caesar cipher was the letter D all over. And the decryption was just subtraction from the ciphertext to get back the plain text. Now, it was realized that maybe this shift, this D everywhere should be different. And maybe we could use something a little bit more fancy. So it took a little while. In around 1586, Blaise de Vigenère invented what's now known as the Vigenère cipher. And so what he did is he basically just expanded on Caesar's idea. And instead of shifting always by the same amount, he would shift corresponding to letters that were selected independently of the message. So this is the key. The key is cod, and so on. And you do the same as in Caesar cipher. You shift the letters by a certain amount depending on the letters of the key, and it gives you a cipher, and you undo it the same way as in Caesar cipher. Now, Vigenère cipher lasted a long time. And to the extent that even in 1841, the great Edgar Allan Poe wrote that it may be roundly asserted that human ingenuity cannot concoct a cipher which human ingenuity cannot resolve. He was of this belief that everything we can invent to protect privacy can be broken somehow if you're smart enough. Now, his idea was seeing a lot about the coming future because in the 1850s, Kaczynski, actually 300 years after invention of Vigenère, was actually able to break Vigenère cipher. I'm not going to go into details of how this is done, but it's basically using the fact that the letters of the alphabet has frequencies, and if you play with these frequencies, you can recover the original message without actually knowing the key. You can completely reconstruct the message. Now, another jump in time takes us to 1923 with a certain German Scherbius who invented a prototype machine which was inspired by Vigenère, where the difference from Vigenère cipher is that instead of repeating a short key, the key would change on and on and on, changing and looking random and so forth. And that machine, you've certainly heard about it, was called the Enigma. And so this machine was distributed as a product from the 1920s. Now, around the same time, in America, Gilbert Vernon invented another scheme which we recently found out was not his original, well, he reinvented it. It was actually invented in 1882 by a banker called Miller in California, who basically described the same invention in a book that was distributed in about 200 copies to bankers around the USA. Now, it was like 10 years ago that we found out about this guy and about his invention, but so let me tell you about Vernon's cipher. Vernon's cipher is wonderful. And I always start my cryptography classes by saying what this scheme is, and then wondering, why do I teach crypto? Because the scheme is so wonderful, it does everything we want, so why bother doing anything else? Well, the scheme can be represented this way. The scheme, you can think of a key which is shared between the sender and the receiver of a message. And this key is completely random. So it's made of black and white pixels that were randomly selected. Now, I started from a message, and I applied an operation to the message and the key, and this is what I got. So this image up here is a ciphertext. It's the conversion of a message using the key. Now, the operation to decrypt, and this is why I use these pictures, can be obtained by simply superposing the two pictures. If you superpose the two pictures, you get to see a version of the original. The original was Vernon. And you can see that from superposing these two images. Now, this is great. You can do that with one message and get a ciphertext for it. You can do that with another ciphertext and do the same. And so this is Gilbert. Vernon's was Gilbert Vernon. And believe me, Vernon's cipher is perfect. Now, this is in 1926, and people didn't know that. People did not have the mathematics to understand that the cipher was perfect. Now, if we have a perfect cipher, why bother? Do anything else? Well, there's a little glitch with Vernon cipher. It's perfect in the sense that if you see an encrypted message, if you see a ciphertext, it tells you nothing about which particular plaintext it was constructed from. You don't know at all what message it was. But if you do it twice with the same key, you get the unfortunate situation that I'm now describing. Someone who doesn't know the key, who sees two encryptions of two messages with the same key, but without knowing the key, can do the same operation using these two ciphers and obtain the following image. Now, it's a little bit harder to see, but this image actually contains Vernon horizontally and contains Gilbert diagonally. You may have heard that Vernon cipher is also known as the one-time pad, meaning that each time you use it, you get this amazing property that it's perfectly secret, but you cannot reuse it. You have to discard the pad, discard the key, get a fresh key, and do it over again. Now, for very important situations like World War II, well, you know, right? You all saw The Imitation Game, and you all know that this made the difference in World War II because the German machine Enigma could be broken. Again, for reasons that I'm not going to explain, it was not a bad idea, but it was used carelessly because they didn't have the mathematics to understand how to use these things properly. Now, on the other hand, Vernon cipher was perfect. They were very diligent about exchanging keys between England and America, and this led to winning the Second World War. Now, in 1948 came Claude Shannon, and Shannon invented information theory, which is the mathematics for understanding ciphers, for proving that Vernon cipher was actually perfect. Now, after this, I make a very short introduction to modern crypto. Then a lot of other things happened, like the data encryption standard, public key cryptography, RSA, elliptic curve cryptography, AES, all these things. But I'm not going to tell you only about crypto, I want to tell you about quantum. So modern crypto has been very popular. It's been tremendously expanding from the 1970s on to now, and now it's pervasive, it's everywhere, we use it all the time. But then in the 70s as well, something extraordinary happened. Cryptography met quantum physics. And it started with this guy, Stephen Wiesner. Stephen Wiesner had this amazing idea that unfortunately for him, nobody understood, that somehow quantum uncertainty must imply cryptographic security. He had this idea that somehow using quantum states, you must be able to hide information in there. And he wrote a paper in the 1970s that he submitted to the IEEE Transaction Information Theory. And guess what? It got rejected. The referees couldn't make sense of it. But he had friends, and this really made history. There's this amazing statement to which Bill referred a little bit. Feynman in 1981 said that if you want to simulate the quantum world, well, you better do it with a quantum mechanical machine. And that's a wonderful problem to work on, and we're still working on it. So I personally believe that these two people really started the world of quantum computing, one hoping to do cryptography with it, and one envisioning that in order to simulate the world, we need quantum computers. Now, by 1984, Charles Bennett, who had been roommate with Wiesner back in the 70s, had heard of Wiesner's idea, and he went to a conference. Well, actually, this is 1979 where this started. Bennett met Brassard at a conference, and they realized immediately how Wiesner's ideas was fundamental. Now, what Wiesner failed was, well, he was not a cryptographer. So he could not find cryptographic applications to his ideas. They did. And so you certainly heard of quantum key distribution. This is what they invented in 1984. I was a student of Gilles back then. I was his master's student starting in 1984. And I heard these guys talk about this, and you should have seen this. First look what they looked like. They were talking to cryptographers. Cryptographers knew no quantum physics whatsoever. And they were wearing like polarizing glasses from Disney and things like that. And so I made this cartoon, this is a fake. I made this analog magazine cover, which never existed, and made it for quantum cryptography, and they really liked it. Now, back then, quantum cryptography was not believed to be possible. Some people in crypto still don't believe in it. I tell you, I still go to these crypto conferences, and a lot of people still don't believe that quantum crypto was useful. Now, in 1985, David Deutsch basically expanded on the ideas of Feynman, and he established the basic principles of a quantum computer and described a universal quantum machine capable of simulating any finite physical system. And this is a tremendous impact on the course of this story. This is what, I mean, you can see the time scale here is short. In 85, for the first time, someone proposes a model of computation on a quantum computer, and by 94, Shor has his factoring algorithm. So things have been moving really fast. Now, around the same time, in 89, Bennett and Brassard built a prototype of their device. Now, still, at this point in time, people did not really realize the practicality of this quantum key distribution. And it took the paper of Arthur Eckert, who established a relation between entanglement and EPR, the Einstein-Podolsky-Rosen questioning of entanglement, and quantum key distribution, where he reintroduced a mechanism for generating secret keys using quantum, but based on entanglement, which Bennett and Brassard didn't use. Now, at first, and I remember this very clearly, at first, those of us that knew about BB84, we were wondering, yes, but what? Why would that make any difference? Why having entanglement involved is a better thing? Because entanglement is just complication in practice. You don't want to, I mean, we're still having trouble generating entanglement nowadays. So imagine back then how we were rebellious to this new idea of introducing entanglement. But it turned out to be so influential because ultimately all the proofs of security of BB84 were in the model of Eckert first and then translated in the model of BB84. It turns out entanglement is the key and it made a tremendous impact. So ultimately, after Ecker's publication and after they published a paper in Scientific American, it became recognized by the physics community that quantum cryptography maybe had a future. And then people started doing experiments, like doing quantum cryptography over a 600-meter channel in 2004, like in open air between two islands in the Canary Islands in 2012. And eventually in 2017 and 18, China was able to set out a satellite that can do quantum key exchange. And they were able to do quantum key exchange at a distance of over 7,000 kilometers between Austria and China, where they had this encrypted video call using quantum key distribution. Now, Canada is in the process of launching its own satellite. So this is a project to which I'm collaborating. I'm one of the users of the satellite, and we're developing some software for it. And this should launch within a year. And we're pretty on time. So I really expect this to happen in 2026. And we're going to be one of maybe 3-4 nations in the world that have a quantum satellite functioning. Now, you may wonder, yes, but what about terrestrial connections for quantum key distribution? Well, in 2023, there was this team in China that were able to do connection through fiber optics over 1,000 kilometers. Now, this is a very new idea using what's called twin field experiments, and it gives a tremendous advancement for the future, because current technology for quantum distribution through fiber is about 400 kilometers. We can do these things at about a 100-kilometer distance. Now, in the meanwhile, a whole industry developed around quantum communication and quantum key distribution. And so in particular, there's all these companies, IDE in Switzerland, MagicQ in New York, Toshiba in England, Kasky and Quantum CTech in China, Quintessence Lab in Australia, Qubitech in the US, QNew in India, SecureNet in France, Qrate in Russia, and QuiQuant and Quantum Optics Jena in Germany. And so all these companies actually sell products where you can buy equipment that uses optics for quantum communication and allows to create keys for classical quantum systems. Now, here's where I entered the story. In 1993, Bennett Brassard, myself, Josa, Perez, and Wooters invented the concept that Bill told you about called quantum teleportation. Now, quantum teleportation, the name was chosen for a reason, and I'll try to tell you a little bit why as we go along the way. I'm not going to describe it in detail, but I want to tell you that the important conceptual step in inventing quantum teleportation was the realization that quantum communication, transporting quantum states from one place to another, can be done if you have entanglement and classical communication. So if you can do classical communication, then you can do quantum communication as long as you have entanglement. Okay, but what does that mean? And why is this, in a sense, special? This is special because quantum teleportation is a process by which Alice at A and Bob at B Alice wants to transmit a quantum state psi to Bob. And instead of physically moving that state to Bob, she will do that by making an experiment in her lab involving psi together with half of an entangled pair. So there's an entangled pair which is half given to Alice and half given to Bob. Alice is going to make a local experiment in her lab involving this half together with the thing she wants to transmit to Bob. And this is going to give her a result, a classical result, 2 bits that she's going to communicate to Bob in an arbitrary way through a classical channel. This can even be broadcast. She doesn't even know where Bob is. Bob could be anywhere. And she can broadcast the classical information, and Bob, wherever he is going to get it. And he's going to use the other half of the EPR pair, apply a transformation dictated by this classical information, and the result of that is going to be an exact copy of psi. So the psi that enters here outputs here, and it's exactly identical as long as this here is a perfect EPR pair, perfectly entangled. Now, why did we call it teleportation? Because the process must destroy the original. It's not just a process of communicating the state, it's a process destroying the original. In the process, when Alice makes her measurement here, she actually destroys the original, and for a certain amount of time, the original doesn't exist anymore. And the only thing that exists are the 2 classical bits that are transmitted to Bob. And these 2 classical bits are actually enough for Bob to reconstruct the state from his half of the EPR pair. Now, I want to point out that the source of this entanglement, the source of the quantum states, can be external to Alice and Bob. It could be Alice herself, and she could send half the entanglement as well as the classical bits to Bob. But more strange, the entanglement could be from Bob, who keeps half of it and sends the other half to Alice. So this means that you can actually use entanglement backwards to transmit quantum information. You can transmit information from Alice to Bob. The information you're transmitting is quantum, but all you need is a forward classical channel and a backwards entanglement source. Now, why do I care? Well, I care because this means that if you want to create a network of communication for quantum information, you don't need every user to be able to inject quantum information in the network. All you need is that the network generates entanglement and distributes it to the users. So this is a little bit like a gas company. A gas company distributes gas to people. They don't get gas from people back into their system. Well, you can do the same thing with entanglement. You can distribute entanglement to everybody, and you don't need them to send you quantum stuff at all. You can use this entanglement together with a classical network, of course, and use teleportation and get quantum stuff to go in all directions. And you can do that by only, so this means that quantum networks can specialize in a very simple, unique task, distribute entanglement. And that's the only thing required by the network, distribute entanglement. And everything else can be done using teleportation. Now, this is a network that's been developed in China between Beijing and Shanghai. You have all these nodes and all these points connect to each other, and they were able to do secret communication using those links from one point to the other. Now, I introduced you a fair amount of crypto, and I now introduced you a fair amount of quantum. So why not merge them? I'm sure some of you have probably seen this before, but some have not. I want to tell you that really quantum teleportation is nothing but Vernam cipher in the quantum world. Quantum teleportation takes a message, let's say, now that's a classical message, but instead I want to send a quantum message. It has keys. The keys are the two halves of the EPR pair. And the operations that you do here is the encryption of the message through one half of the key. It generates a ciphertext that are the two classical bits. And notice that when I generated the ciphertext, I destroyed the original. That's exactly what it's doing. Now Bob receives the ciphertext, he uses half of the key, and he reconstructs the original. And this is, I tell you, mathematically, this is exactly Vernam cipher applied to quantum states. Which means that all data transmitted via quantum teleportation is inherently Vernam encrypted. If you deploy a near perfect quantum entanglement distribution system and you work really hard to make these entanglements really strong and really good because you want your clients to obtain good transmission, at the same time, you secure all their transmissions. So if you use quantum teleportation as a mechanism to transport quantum information around, you don't need any kind of extra security. It's already completely encrypted. All the classical bits that are transmitted are purely random and totally useless. Now, I just want to finish my story by telling you another thing you might not know. This guy here, Dan Simon, in 1993 also, invented an algorithm which preceded Shor's algorithm in the sense that Dan Simon was a postdoc in Montreal at the time. Dan invented an algorithm which used exactly the mechanics to calculate the length of a long period in a cycle. And this is where this idea came from. Now, he submitted his paper to a conference, and Peter Shor was one of the referees of this conference. And he saw this paper, he encouraged the paper to be accepted, but the other referees didn't. So the paper was turned down. And so over the next few months, he realized that this idea of Simon had an extreme value. So he contacted Simon and he asked him if he wanted to join forces with him and work on this. Well, Simon said, let's submit both our papers to the next conference. And if both get accepted, let it be this way, separately. And if not, I'll join forces with you. Now, of course, both papers were accepted. And this is how Shor's algorithm was invented. I'm not making this up. There's a writing on the archive where Peter Shor describes this literally. And the impact, I mean, I agree with Bill, there are many other applications of quantum computer, but the existence of this algorithm motivated the race. It motivated that we must build a quantum computer. We need that. And if we do, then all the crypto we're currently using, everything public key and so on, is destroyed by a quantum computer. So there's a big problem. So there are two things here. On one hand, quantum promises it's going to be great. If you do everything using teleportation, everything's encrypted, it's fantastic. On the other hand, the crypto that's currently used is wiped out. And there is time between now and the time where a full-fledged quantum computer is built, and we're lucky. We're really lucky, because if 5 years after Peter Shor's algorithm, it was discovered how to build a quantum computer, we'd be in a terrible mess. Because for a long time, this principle has been going on. The harvest now and decrypt later is the principle that if you're powerful enough, and I'm not going to name any countries, if you're powerful enough, you're going to store the information of the internet. You're going to store all communications going through the internet and just wait for a future where all the encrypted stuff becomes readable. This is the harvest now part. And when Shor's algorithm is implemented, the decrypt later part. And this has been going on, I swear to you, this has been going on. And we need time to stop using these systems, because 15, 20 years from now, there will be full-fledged quantum computers, and all these things that have been harvested even today will be decrypted. Do I have much to hide? No. Does my government have a lot to hide? Yes. Do banks have a lot to, I mean, a lot of situations should not be decrypted. Now, this led to what we call post-quantum cryptography. So post-quantum cryptography is, again, the type of cryptography that relies on cryptographic assumptions. And there's this contest going on that started in 2017. There were all these systems submitted. Some of them were withdrawn right from the start. But this process has been going on, and a few winners have been identified. And, okay, great. So let's continue the same business as before. Let's change the system to a system that quantum computers don't appear to break. And let's use them and not worry. And the same people who promote that say quantum cryptography is not such a good idea because it's costly and it's complicated. Okay? Now, well, something funny happened, because one of these systems actually was cracked. It was in the final stage, accepted all the way through, and then it was completely cracked. Not even by a quantum computer, by a completely classical algorithm. Someone found how to break it. It was broken. Bang. Oh, okay. Well, we had a bad case. Well, okay. Now, listen to me. Harvest now and decrypt later will keep on going. Now it's through RSA system. Then it's going to be about LWE, lattice-based systems. All these systems have the same weakness. There might be, on any given day, someone who finds an efficient algorithm to solve the problems behind them, and then suddenly you have no more security. And all the harvesting you've been doing for 10, 15, 50 years, you can just crack everything. So my situation as a cryptographer is, yes, we have to move to post-quantum cryptography. We have to change our systems because they're weak, but we have to do better. We have to go all the way to quantum, and we have to get these networks built. So let me conclude by making local publicity. I was at a meeting this week for a project called Kirk. Kirk is a quantum testbed for quantum cryptography and communication. It's run by Numana, which is a Montreal-based Quebec's government baby. It's a semi-governmental organization that receives some funding from the government and some funding from industry. And they have been in charge for 2 years now for a project of establishing a network of quantum communication in Quebec between Montreal, Sherbrooke, and Quebec City. And they are in the process, well, right now they're testing quantum key distribution equipments that they obtain from manufacturers, and the later stage will be to deploy entanglement communication and eventually do teleportation on this network. Now I conclude with answering the question. I do believe quantum information is a friend to privacy, a lot more than a foe. I do believe going quantum as fast as possible, especially in terms of communications, is the way to go. I thank you very much for your attention. It's been a pleasure.
So thanks so much for these two talks. We actually have time for maybe a shorter Q&A session that we planned. So if the two speakers want to sit down and you can ask any question. I only ask you, we have microphones. McGill unfortunately doesn't have wireless microphones, so if you could repeat the question when coming back, that would be awesome. And so anyone have a question? Let's get started.
Yeah. Could you please come in front if you do have a question? Thank you very much. Did you use this?
I could go around and use this, but this is really not. I think it's for anyone comments. If someone is not reachable, I'll comment.
Thank you so much for the talk. I just want to test. Yeah. Okay, I'll try to I want to ask a little about the entangled pairs that are used as the key for encryption. So what are they look like? Are they photons? Are they electrons? How do you distribute them? What is that system look like? Is it?
Okay, well, I can start and probably Bill can correct me. But the most common ones, as far as I know, are photon-based. You can use nonlinear crystals that have the property that if you flash some light at them, they will create a pair of photons from the point where it receives the light. It will split a single photon with a higher energy into two photons of lower energy that are entangled. They're not all entangled, but there are particular locations outside this crystal where the photons are entangled. And that's a reliable source of entangled photon that you can use in these experiments. It's also possible in electronic systems and so on, but from my perspective of quantum communication, this is the most common source using these nonlinear crystals.
I have one other question. Okay. I have another question about quantum computers. What is the output of one look like? Is the output also in a quantum state?
So usually you want an algorithm that is deterministic. So there are two types of quantum algorithms. Those that can give you regular classical output, zeros and ones, and others that give you a statistical distribution of outputs. So you might have to run those ones that give you a statistical distribution of outputs a few times to get more information about the answer. But if you have a deterministic quantum algorithm, just like a regular computer will take a definite answer in and give you a definite answer out, that quantum computer can give you the same answer out or the same answer in every single time. There are certain algorithms. So you may be asking the question, okay, how can it be a quantum system has these multiple states at the same time, has superposition? How can it be that you get a definite answer out? And the answer is that sometimes the quantum superposition or the interference that happens gives you a perfect destructive or perfect constructive interference at the end to give you a perfect 1 and 0. And that's the situation for deterministic algorithm. Is that answer? That answer your question?
Any other questions? May I please come to this? Please go ahead.
So first I want to say thank you for delivering the talk. It was really educational. You're both great speakers. Dr. Coish, I just wanted to ask more about the bit that you maybe didn't have enough time to speak on, which is how your lab creates like room temperature coherence using classical light.
Okay, I'm a theoretical physicist. I should have made that more clear. So it's a concept, it's a proposal, but it's based on sound physical reasoning. So the room temperature aspect of it is that you can do measurements at room temperature for the types of quantum states that we're producing. Whereas if you want to measure single photons, very often you need low temperature cryogenic measurement apparatus. So I think I shouldn't go too far into the detail, but I can tell you a couple of words. So there is a property in physics that if you have a charged particle that's accelerated, it goes back and forth, it emits light. Okay, so an accelerating particle will emit light. If you shine light into a quantum cavity, it can generate a kind of oscillation in the electromagnetic field. If you oscillate a charged particle in a quantum cavity, it generates an oscillation in the electromagnetic field. And when you shine light on a quantum cavity at the same time as you accelerate a particle inside the quantum cavity with the same amplitude and phase, you can get perfect destructive interference that allows reflection. Now, if you have the situation that you're accelerating that particle only if your qubit is in one state, and you're not accelerating the particle if your qubit is in the other state, then you can prepare your qubit in a superposition of excited and ground states, so those two states. And you get a superposition of those two effects, one where you get perfect reflection, the other where you get perfect transmission. And that can work, or in fact, it only works with classical light. Not single photons, but classical pulses of light. So you get classical light through, classical light reflected, and then you can play all the games you can play with classical light instead of doing the single photon.
I don't know. Do I speak loud enough?
Speak loud, or if they could repeat the question.
With regards to the transmission of encrypted video call between Austria and China, were they using some sort of quantum teleportation-based system, or can you go more in detail on how they did it?
Okay, so they were not using quantum teleportation, they were using quantum key distribution. So they established some classical keys using exchange of quantum data. And in so doing, they generated secret keys that, I mean, they cheated a little bit on the crypto. Okay, so they use secret keys in a system that's computationally secure to protect the conversation, because video is a lot of data. But for the time of the experiment, it was very secure. But the physics of it was essentially exchanging single photons from Earth to satellite. As a matter of fact, you prefer to do it from the satellite down to Earth, where you can use like astronomical telescope as a receiver. And so the source is in the satellite, and the reception is on the ground.
Thank you very much.
why is the distance regarded as a milestone? Like if 7,000 kilometers is a bigger deal than 1 meter?
Very good question. For quantum systems to have the properties that will give you security, you have to use them one by one. In particular, in light polarization, you have to send single photons. So you're not sending a beam of light, you're actually generating a very, very weak source that sometimes generate a photon, and it's this photon that you want to get all the way through to the other part of the experiment. And it's this that gets a big limitation. It's a lot easier if you send it to space, because after a few kilometers of air, you have pretty much nothingness until you reach the satellite. So it's a lot easier than at the ground level. But in fiber optics does absorb some of your photons every once in a while. And the current standard is about 100 kilometers. The industrial products that you can buy these days will function at a distance about 100 kilometers. And the fact that you can do it at 1,000 kilometers, as in the experiment that I described, that I named, is extraordinary. 10 years ago, nobody would have believed that possible, because the characteristic of the existing fibers don't allow you to go that far with a single photon.
Thank you.
Okay, so you mentioned in your talk the harvest analogy quick layer practice. Is there anything we can preferably do to combat that? Because from my mind, it seems that until we develop quantum cryptography to a certain level, all of our data right now has already been compromised by some user actor.
Well, as far as I can tell, there are several systems out there. And if you combine the existing systems, if instead of just using RSA now, we decided to use RSA and 2 or 3 of its competitors and combine them in such a way that you must break them all before you can decrypt. Of course, that would slow things down by a factor, say, of 5, because you would have to run 5 systems instead of 1, but you can do that in parallel. You would extend the period, because before they're all broken by the strongest of them all. And that's definitely something that we can do already, and that nobody does, because nobody seems to care about security to that extent. But it's something that one can do perfectly. The proposals that I showed, there are several of them. You can use them all if you want. And it's not that complicated to combine several systems together to get one which is as strong as the strongest. And so that's definitely one way to go if people really care about security. You can do better. You can extend the period of security maybe from 50 years to 200, 500 years, if you're lucky enough that one of them survives for all this long.
I was just wondering, how do you get a quantum computer to run whatever instructions you're trying to get it to run?
So you're asking, how do you enter the information? What
Yes.
is the kind of interface that you use?
Yeah, exactly. Like, I know you can code on a classical computer. How would you get the same kind of thing to run on a quantum computer?
So there are online systems now where you can access quantum computers via the cloud. And so IBM has been running one for quite a while. It used to be called the IBM Quantum Experience. It's changed its name. I forgot what it's called now. There's also Amazon Web Services. They have a quantum interface, just a web interface that allows you to make quantum algorithms and run them on their system. And these things can run on real hardware. So they run on superconducting qubits for the IBM system. They can run on ion trap qubits or superconducting qubits for the Amazon system. But the size of the quantum computers that you have access to as a normal person is much smaller than the 100 qubit system that I showed up there. It's on the order up to about 16 or 20 some qubits. There's also one now in Quebec from Enion Systems that is based at ETS.
At Calcul Québec.
Quebec, yeah. I don't know if it has a public interface, but it does have access for academics if you make an application, I believe, right? They're
Jacob, you know more than I do.
All I know is it's under our feet on campus cloud.
Yeah.
Okay.
So, so there are many options. There are web interfaces and people have written software. So several of the companies that I talked about, they have their own software products and everyone is trying to sell their own interface software. So you can, a quick Google search will send you all over the place looking for interesting ways to get interface quantum computers.
Thank you.
Just a question about encryption generally. Meta on, say, Messenger will tell me this is being doubly encrypted. People are sending pictures of cats. Why are they just generally encrypting nonsense messages? Like, why are they just assuming that it's worthwhile encrypting everything?
Well, encryption has a cost in the sense that it slows things down. It uses processors that could do other tasks and so on. And so it doesn't seem necessary that you encrypt everything all the time.
But Meta does it to my messages.
But sorry?
Meta.
Facebook,
Facebook
Meta, the parent.
encrypts, it just tells me your message is being doubly encrypted. So like at the beginning and at the end, and it's not necessary for
A vast majority of,
the vast majority
Yes.
of usages.
well, that's marketing. I mean, make it sound fantastic and people will think that you're on their side. I mean, basically, it's their statement that they want to convince people that they do the right things to protect them, while on the other side, they don't really do it. So it's marketing. Unfortunately. Peter.
Yes, thanks very much for great talks. And so your statement should be worried about privacy and quantum, given the fact that all the companies or most of the companies that Bill mentioned are data suckers, like Amazon, Google, whatever they name. And they're also the builders of the quantum computers who they decrypt all my information and everybody else's information and all the marks that we store somewhere on the cloud. And
Well,
should I be worried or not?
of course. I mean, we cryptographers don't sleep at night.
So what should I do?
Build a quantum computer. I mean, but I mean, physics gives the answer, right? The no cloning theorem means that if you have your data and you keep it, then nobody can get a copy of it and you not knowing about it. And that's something that classically is impossible. And this is going to make a tremendous difference. And the more quantum we get, the more security we get. Because of the structure of quantum mechanics, it's a gift. But I mean, but otherwise, on the more maybe pragmatic day-to-day life, we should worry about our privacy more than we do. I mean, we broadcast our lives. I do too, right? I mean, but I don't broadcast everything about my life.
I fully agree with what Claude said, that we do have to worry about it in the long term. Probably the situation is not so bad for the next 10 to 15 years, if you give my best estimate. But you did notice maybe on the graph of the expert's opinion, people are saying there's about a 15% chance that we get a quantum computer that can crack these codes within about 5 years. And that was a survey that was done 2 years ago. So there is a danger. It could be that there's a breakthrough that allows it to happen, and there is far more money in the game now than there even was 5 years ago.
So, I would add.
Yeah.
I was wondering, when you have the the entangled particles that you send to the user, how do you know that those entangled particles aren't intercepted, or like the key is occupied?
Right, so entanglement is great because you can test it. So and in a futuristic world, I would imagine several companies broadcasting entanglement. And I would go to whoever provider gives me the best quality entanglement. And I can test that. So I can test with my friend, we receive continuously entanglement from this company, and every once in a while, we don't use it, but we actually test it instead and check for the quality of the entanglement that we get. And if you have a computer on your own and you can run these experiments, you can establish that this source is reliable. I'm not sure it's always reliable 100% of the time, but I can make operations that will distribute my information in such a way that if the source is regularly unreliable, I'm going to detect it. If the source is very sparsely unreliable, then I can correct that and get my data to be secure in the end anyway. So it gives you the mechanics to make sure, even if you don't trust the source, that what you get from them is useful and reliable. And that's the beauty of it. Because you can buy entanglement from your enemies if they sell it cheaper, because you can just test it. And if they're more reliable than your friends, who knows what your friends are going to do next day anyway.
Classical cryptography is implementable in software on general purpose computing. Unless I misunderstood something, quantum cryptography is going to require specialized hardware.
It depends what you mean by specialized hardware.
Well,
specialized hardware today is not specialized hardware in the future. I mean, if you use satellite, for instance, your amount of, you don't need a wire from point A to point B, but you can use a satellite to receive entanglement and things like that. I mean, of course, it requires new machine, it requires new communication systems, it requires a lot of new things. But these things are in development and some are in deployment.
Yeah, but if we manage to break RSA before this specialized hardware is available, there's going to be a gap where things are going to be very, very messy.
Well, that's why post-quantum cryptography needs to be pursued. I mean, it's a major thing right now to use these post-quantum systems and move up to systems that we do not know how to break using quantum computers. This is a top priority. I mean, if you have data and you need it protected, you can't wait for the quantum infrastructure to be ready for you to help you. You have to move right away and get started using open source or whatever implementation of these new post-quantum primitives that are available, and you have to start doing that. That's 100%. But I think that on the longer run, we would like to do even better than that.
Two more questions, I think. Yeah. Thank you for a very interesting evening. What distinguishes the signal application that we've been hearing about lately? Is there a proprietary algorithm? What makes it so visible now? That makes it unique? Is there something special about the application that can?
It's interesting that you say that. You said proprietary. Well, you said it right, I didn't, but it's okay. Because there's this wrong impression that good crypto is secret crypto. On the contrary, the best crypto is the crypto that everybody knows about. If everybody knows and understands the system, then everybody can attack it. And if you fail for 50 years to break a system that everybody understands, it's a great system. If you fail for 50 years at breaking a system that you don't know, well, it might be that the next day someone will learn about the system and break it readily. So it's not that they're using something secret, it's that they use the crypto in a better way. They use point-to-point encryption at a high level quality, and everybody else could develop an application like they did.
What's quality?
Well, quality is use larger keys, which means slow down your process more, but get more security. I mean, for instance, with RSA, you saw Bill's figure, right? If you use 1024 bits, it's going to be 1 second or 1 day. One day, right? If you use the double size, it's going to be millions of years, right? Well, if you double again, it's going to be several times the age of the universe, what would be needed to break it. So if you want to get more security, use larger keys. It's going to slow down your processes by, well, if you double the size, typically it's going to slow down by a factor of 4 or something like that. But the security you get is a lot more. And so it's always a threshold. Do you want more security or do you want more practicality? If you want to be more practical, then you're going to decrease the security. Everything's going to run faster, but you're just going to be wishful thinking that the security resists. If you really want to be secure, you can use larger key size. You can use more systems. There are simple things you can do to get more security, but nobody's going to buy it because your system is going to be tremendously slower than your competitor. It's all about how much do you care for it. And if I were a government, I would use the top level security always. And so I heard today, I didn't know, but apparently Signal have been accepted as a valid means of communicating government information.
Just you can just
Unofficially.
information.
Yeah.
Thank you.
Okay.
Okay, so one last question.
Yes, what about the artificial intelligence in your field? Do you, or what's the implication?
It's a very nice question. Artificial intelligence plays some very important role in the world of computer security in particular, because artificial intelligence can detect patterns where we humans don't detect patterns at all. And there are lots of nowadays security systems to detect attacks on systems that rely on artificial intelligence. That's definitely one direction where it's very popular. And it's a tool to security. On the other hand, quantum computers appear to bring something to artificial intelligence. So on the other extreme, quantum computers seem to be favorable to AI. And so AI people are really interested in getting quantum computers developed because it will mean faster and better systems that can do even better AI.
So a simple way to understand that is that a lot of what goes into making a good neural network is a training procedure or an optimization procedure. Quantum computers seem to be very good at optimization problems. And so if you can encode that training in the quantum computer or use the quantum computer to train the neural network, then there is evidence that there are significant advantages.
Is it dangerous?
Sorry?
Is it dangerous?
Is it dangerous to improve AI with quantum computers?
Open the door.
I think this is an unknown danger. I think that so breaking crypto systems is a very well-known danger. And AI has a wealth of unknown dangers. Not just quantum AI, but of course other types of AI. There we don't know the dangers, but for cryptography, we really know very well what are the dangers.
Because they talk about black box and stuff like that, which is, I don't know what, but they seem to be clear about that. In AI. So,
Well, ultimately, we don't know how far AI is going to go. I mean, ultimately, AI could be a lot more intelligent than we are. So what do we know, right? How can we control it? And we have to be careful. And that's why you have voices out there that say, okay, development of AI should be somewhat controlled. Like we control research in medicine and we control research in biology, because we don't want to destroy humanity by doing just arbitrary experiments. Well, AI should be part of that. That we behave and we're careful in what we're doing. We don't allow everyone to do whatever they please.
but you guys are developing a computer.
But you have to understand something. That computer will come whether we develop it or not, in the sense that we know it has purposes that are not nice. So it's much better to have that computer to defend and to have the powers to protect yourself, because we know the bad guys will get it anyway. So if I can convince you that we can get more security through quantum computers, this is the bright side of it. And we know the bad guys will develop a quantum computer to break RSA in 20 years anyhow. So we have to be realistic. We can't just say, I'm going to shut my eyes and it's going to go away. It's not. We have to be realistic and say, well, the world is changing this way, and we have to be part of it.
Okay, let's thank our speakers once again.
Yeah, before you all leave, I wanted to make a quick announcement. So first of all, we have something going on in our physics department next week, which is part of the Anna McPherson lecture series. So it's going to be on April 3rd and April 4th, and it's open to everyone. And then as a last announcement, sorry, here, or I think I'm just going to say this in person, is that our next panel is going to be on life on Earth and beyond. So we're going to explore potential search across Earth, of course, and on extreme environments such as Mars, Europa, and Titan. And yeah, you're all welcome to join.
Okay, it's coming.
It's coming.
Yes.
Okay, anyway. So if you're interested in joining, it's free and it's open to everyone. Thanks again, and thank you so much to our two speakers. This was fantastic. Thank you. So if your name is Veronique, you won the raffle. Sorry, and it's absolutely.
making laugh. When you were showing that the Caesar
Yes.
picture, it reminded me when I was in the 70s. I didn't want my mother reading my diary.
Uh-huh.
So I had this code,
Oh, yes.
like this is my name, says Claude.
Yes.
You know, she would be like, what the heck are you writing about? So I just wanted to make you laugh. I was doing this in that 60s.
Good for you.